Okay. Next session will be delivered by Dr. Biswajit Sahoo. জানি পচারো।
Hello, ma'am, should I start?
हाँ Biswajit, Dr. Biswajit, you can start. It
Okay.
perhaps
Am I audible?
actually
Yes,
Dr.
sir.
Biswajit is actually a AI engineer, so he can talk better than us. That what is the application of real life in means what is the application of all the components in industry 4.0 or 5.0, like what is AI, ML, digital twin, how it will be implemented. So please deliver, Biswajit,
Yeah.
Dr. Biswajit.
Thank you, ma'am. So let me share my screen. Is my screen visible?
Yes, sir.
And are the slides moving?
Yes.
Yes, sir.
Okay, thank you. Thank you. So, yeah, hello everyone. Good afternoon. So, today in this talk, we'll be covering about manufacturing systems that are essential for Industry 5.0. So, in this talk, I'll be giving some examples, and mostly it would be HP specific examples. So, yeah, we'll go through that. So, first, as the outline, we'll cover some emerging trends that are currently popular in manufacturing. Then we'll briefly go over additive manufacturing. And here I'll mostly cover how HP's additive manufacturing 3D printing technology works. So, then we'll cover something called generative design and how we use that in practice. So after that, we'll cover some examples of cyber physical systems. Here also, I'll give another example of how HP is using cyber physical system in its own 3D printing technology. Then another recently get another technology that is recently getting used is AR VR. So here again, AR VR and automation. Here again, I'll give some examples of HP, how HP is using it in practice. So yeah, please let me know if my voice goes down at some point. Otherwise, I'll start with this.
No,
So
it
yeah,
is okay.
yeah. Thank you, ma'am. So yeah, so coming to the emerging trends that are popular in manufacturing these days, obviously additive manufacturing is at the top of the list. So it provides many advantages to us as compared to traditional manufacturing. Yes, traditional manufacturing gives us high finish or tolerance. The greatest tolerance we can get is from traditional manufacturing, and we can also produce products at a mass scale. So if we need, let's say, 1 lakh products or more than that, maybe traditional manufacturing is good. But the use of additive manufacturing becomes essential when we require to design complex parts that our traditional manufacturing process can't handle. So at that point, will be this additive manufacturing process becomes very useful in our day-to-day practice. So uh, we'll see some examples how that happens and how HP is working here. Now then, recently these generative design tools and topology optimization tools are becoming very popular. The main advantages of using generative designs is here we don't have to manually create a design ourselves. We'll give the specifications to the let's say deep learning model or topology optimization model, and then that model itself would generate a design for us. so that we don't have to manually specify how much should be the diameter at some place, or how much should be the width at a particular place. So these kinds of things we don't have to do design ourselves. Rather, the model would be giving us these values. So how it helps is, whoever is not a expert in that domain, they can use these tools to create the designs of their requirement. Next, the use of AR/VR. By AR/VR, we mean augmented reality and virtual reality. So, how these things are getting used in manufacturing, and how is it helping our day-to-day manufacturing practice? That we will also see. Then, fourth one is adoption of cyber-physical systems. So, these days, people are building digital twins that are digital replica of physical systems. So, how that digital twins are getting built and how it helps in practice, that we'll also see. Finally, how automation and robotics, those are getting used in manufacturing, how that is helping different companies, that we will see. And as an example, I'll give one example of HP specific products. So first we'll see how additive manufacturing helps. Now, before we go to additive manufacturing, we'll see a difference between 2D print and 3D print. So 3D printing is also called additive manufacturing. Why that is called additive manufacturing, we'll see in the subsequent slide. But if we just compare what happens in 2D printing, that is your photo printing, and what happens in the 3D print. In the 2D print, we take the photo in a camera, or we scan the photo, or we directly get the photo from the internet. Then we this modify, we sometimes add some filters, or if we modify, edit few things, then we convert it to a particular format. Usually that is a JPG format, or PNG format, or JPEG format, like that, or sometimes SVG format. Then that photo gets transferred to the driver, printer driver, and then it gets printed in the actual format, actual photo printing paper. In the 3D printing case, what the equivalent is, we have to create a 3D model first. So there are some softwares available like SolidWorks, CATIA, and there are some open source tools also that we can use to create these 3D models. Similarly, there are some open source even websites are available that can create 3D models for you. Simultaneously, there are also scanning tools available that can scan and create a 3D object out of it. Now, once we get a 3D object, we modify that. So modify means we check whether that file has some defects or not. And if there is any defect, we try to rectify those defects. And after that process is done, we get a format, get the files in a particular format. Usually it's called STL format. So that is popular, and there are other formats as well, .3mf format, .obj format, and there are many more. But STL and 3MF are quite popular. So once we get that, it doesn't get directly transferred to the like in the 2D case, it doesn't get directly transferred to the printer. Rather, we follow a step called slicing. That we'll see what slicing does. And after slicing is done, it gets passed to the driver. Then it goes to a 3D printer, and finally we get a 3D printed part. Now, if we come to the additive manufacturing technologies, so there are many ways in which additive manufacturing can be done. So one is the most popular one, I would say is that material extrusion, that is also called FDM, fused deposition molding. So it is the cheapest among all, and it produces reasonable looking parts. But it is not the only way. There are also powder bed fusion techniques, material jetting techniques, and then binder jetting techniques and all. So HP currently focuses on MJF, that is a powder bed fusion technique, that is called multi-jet fusion. So how that is beneficial as compared to others, that we will see later. But in this talk, we'll be focusing mostly on how MJF works, and how it helps in creating complex parts. Now, in the last slide, we saw a process called slicing. Let's say this is our design of a 3D model. Then what slicing does is it slices, it divides that 3D part into a smaller and smaller pieces. So each pieces, horizontal piece, we can say it's a slice. And based on the width or the width material width, the slices numbers number of slices might vary. It might be 100 or it might be 200 depending on the how much width that we want to keep. So it starts like this: we build a 3D model, then we do that slicing part, and slicing just divides that or converts that 3D model into smaller slices. And after that, in this case it is a FDM, so that prints it layer by layer, because the process happens layer by layer, and one layer above one gets added to the layer that is below it. That's why it is called additive, because the layers get added one over another to create that full part or full object. So this is how the 3D printing usually works. Now we'll see how HP 3D printing works and what we need to do to make it work. So if we see, there are many components in a HP 3D printer. So that printer is only this part. Now that printer, because it's a powder bed fusion technique, we need powders to build that. So there is a material handling unit that handles basically the powders that are used in HP printers, and there is a build unit. So actually in this build unit the printing happens, and this build units gets inserted to the printer, and the printer works and printer prints in this build unit. Then we have another part called automatic unpacking station. Once these parts are built, we have to unpack those parts. Unpack means we have to remove those parts from the powder. So that is the work of this unpacking station. Now there is one more unit called natural cooling unit. So once we unpack those parts, we put it inside this natural cooling units for it to cool down. So the if we just see the amount of time it takes, so uh, to pack those powder, you have to put the in the material handling unit. We have to put powders into this build unit. This just to put the powder in build unit, it takes around 3 to 4 hours. And for printing, if we are planning to build a full set of parts, or to the maximum specification, if you want to build, it would take 11 to 12 hours per printing page. And for unpacking it is faster, it may take 1 hour or so. Then if we put it in natural cooling unit, here it is usually cooled down for 24 to 36 hours. Then the part is good for use consumption. Now, for the 3D printing system to work, all these systems should work in tandem. So HP has proprietary software that controls different parts of it. So once we put this build unit in the material handling unit, then it would be automatically packed. And this packing also uses powders, new powders as well as reused powders. So now coming to the advantage what HP provides as compared to other 3D printing tools. So one is the material that gets used is reusable. For example, we can use a new powder as well as whatever powder is left after we print one build, then those reused powders can be used as well. Now HP uses a technical multi-jet fusion that is 3 to 4 times faster as compared to fused deposition molding or the techniques. That is another advantage. And the third advantage is the time that it takes. So time and accuracy, the finished product is better than as compared to the fused deposition molding or other things. So here in HP printers we can get the tolerances up to 90 micron. So if our part dimension is more than, let's say, 3 4 centimeters, we can get tolerance up to 90 micron. Now this is how it works. So there are, as I said, there are material powders are there. So these circles you can think of as material powder units. Now first a powder unit or powder layer is spread over the bed, that is called material recoating. And after that it is just heated down to temperature, to a higher temperature, because if we heat it down, then after that it would be easier to cool it, easier to melt that powder. So that's why this is the powder at the room temperature. But then once it is spread across the bed, we heat it that in the printer, so that the temperature of the powder increases. Then there are two agents. So one is called fusing agent, one is called detailing agents. So fusing agents basically binds those powders, and it is applied at the locations where we want to melt those powder. And detailing agents are just used at the other places where we don't want to melt the powder, because we'll increase the temperature in the printers. And this fusing agents actually work as a absorbing agents. So wherever it is placed, once heat is applied, those powders would be fused means those would be melted, and it would be a single solution. Now, wherever these detailing agents are applied, those parts will not melt. And so, wherever you want to create a part, 3D part, so we put those fusing agents there, and we then melt it. That's how the process gets repeated, and we get a 3D printed part. Similarly, this was for how polymer parts work, because these are powders, means polymer powders, mostly plastic powders, and we heat it and melt it. Now, there are also HP technologies to print 3D 3D metal printing. So it can print steel parts. So there, in that case, steel powder is used. So here also there are many parts that get used or that work in combination, so that so as to produce that uh, uh, metal parts. So here this part is called the printer, where the actual printing happens. Similar to the polymer thing, here also there is a build unit available. So here inside this, the powders are kept, and it gets inserted to the printer, and then printing happens in this. And similar to the polymer part, there is also a powder management station. So using this station, this powders are inserted into the build unit, and then after they are removed as well. Now after that, there is a curing station. So after printing happens, then for metal cases, they also get subjected to a higher temperature, so as to remove any moisture from the parts. And after that curing is done, then it goes for powder removal. So once we remove those powders, then it we get a green part, that we call a green part. And those green parts are then used in sintering to generate actual final parts. So like the original polymer part, here is how the metal jet works. So here we spread one layer of powder, and then it is also applied with some heat to increase the temperature of these powders. And here we put a binding agent. These are called, not called fusing agents, these are just binding agents. So binding, it just binds those powders, and once you add some heat, those it creates a compact powder mix. And after evaporation, the heat is applied to evaporate the moisture out of the other parts. Now after this process is repeated multiple times, after that we get a cured part. And then this is the curing stage, so where we apply some more heat to remove the extra moisture that is available there. After curing, it goes to depowdering, so that basically removes the other powder and just keeps the part, green part. And this green part again goes to sintering unit, where it is means the heat is applied, high amount of heat is applied. uh, the temperature goes above 500 or 600 degrees. Basically it changes the microstructure of the part, and it creates a solid part. After this, then that solid part goes through the cooling phase. After that, it goes to finishing. And this is how these binding agents get inserted. So in the solid, in the metal case, we apply a binding agent, and in plastic case there are two agents, fusing and detailing agents. So these agents are applied through print heads, and these print, this particular example is from a metal jet printer, but similar printheads are also used in polymer printers. So this dimension, as you can see, it is 10 centimeter, and there are multiple printers. These like in a single layer, there are 6 print heads. There are there, and within print head, the resolution is 1 by 1200 inches. So in 1 inch, these print heads can put 1200 drops. It can insert. and it moves in this direction. The scan direction means this moves from this direction to this direction. So uh, how this works is these print heads uh, allow us to put those binding agents wherever you want, and it is with high resolution. As you can see in 1 inch, 1 inch basically is corresponds to 2 centimeters, close to 2.69 centimeters. So within those 2 centimeters, these nozzles, they can drop 1200 drops. So that allows HP to get high part finish also. Now, these are some sample products. These are polymer products that have been generated by 3D printers. As you can see, these are very complex products, and they are prepared in a single go. It doesn't require any assembly or any other things. We pass and these are produced through powders. Similarly, for metal parts as well. Here, for example, this part, it would be very difficult to produce it through machining, for example. But in 3D printer, it can be produced in a single go. Now, how do we design these things? So basically, somebody has to design these kinds of parts. Now, another interesting area there is how can we generate this through using some generative tools or generative design software. So how this generative design works is, so we first define a design domain, what we want to do, what is our raw geometry. Instead of designing, we just specify what is the material used, what the performance is expected of the part, and what is the functionality of the part. Once we know these details, we pass it to a language model in this case, and that language model works as a DFM stands for design for manufacturing expert. So once we specify these things, it comes up with some instructions, and sometimes also we have to do some alterations based on our requirement. This natural language model can give us something else. So if we want to modify a few things, we can modify these specifications, and then it will be generating a new type of design. Now once we get a design, then that gets converted to either a CNC machine, or it can be directly passed on to a 3D printer as well. 3D printer takes those STL files. So if it generates that STL files, you can directly pass it to a 3D printer, and then we can get it printed. Now, this is how it works. So first, we give a text-based prompt to the LLM. So we give them some design bounds for evaluation as well. Now the LLM comes with a functional generation of the material, and then it also refines its outputs based on the requirements. It defines the outputs, refines the outputs, and after everything is done, it generates also some validation criteria, whether the part would be able to withstand the amount of load that we want it to withstand or not. After this kinds of this also validation happens in a loop. So we give our inputs to the LLM, in this case GPT-4, and we return get back the generative models as well. And once we get these models, then we can directly pass these models for our thing, for our 3D printing, or even for CNC machine. Now one important criteria there happens is, we get sometimes this 3D objects, 3D models directly from the LLM. So after that, is there any scope for optimization? So one of the popular techniques that is used in industry is called topology optimization. So what it does is that, given a requirement, can we come up with a simplest design that takes less material, but still that is able to withstand the amount of load that is subjected to. So that process is called topology optimization. So it starts with a black box. So here we just specify how much load. For example, we need to design a bar that should support this side load, that let's say this is of 10 newton or some other value. Now it has to be fixed at one end and free at another end. Now with that we start, and this is a black box to start with. Now we discretize that into smaller grids. So that basically helps. We know the loading condition, external loads and support conditions. Now we discretize that domain. Now after that we optimize that. So basically our goal is wherever the load is applied, it should be able to withstand the high amount of load there, and then other places it should be it should experience lesser stress. So with this we try to optimize the design space. Now after few iterations we might come up with something like this. So this is a completely new looking part where wherever there is no material needed, it is empty, and wherever the material is needed, there is a material present there. And if we use this, this also is able to withstand the amount of load that is expected of it to handle. Now, one advantage of this is this uses very less material as compared to the original block design. The initial black box design, that is just a bar of material with some width, height, and depth that can withstand the load. But here there would be a wastage of material. So, but in the topology optimization case, after we build this design, there would be very less material use. So there would be no wastage of material, but still it would be able to withstand the load. So that is the advantage that topology optimization gives. So one more example of that is, let's say we start with this kind of design. Here it serves our purpose, but there are some extra materials out there. As we see, if we do an FE analysis of this, here most of the things are green. So there is no point in the material where the stress is going above the limit. There are few points are there. There are some stress concentrations are happening, but that are within the limit of the material. So there is no likelihood of any failure happening. But if we do the topology optimization I discussed in the last slide, then that might come up with a design like this. So here, as you see, some places there is of course less material used in this new design, but there are some red regions where material can experience higher stress as compared to its design limits. Now we iterate this process over and over multiple times, and we change the constraints also. If at this point the material is unable to handle the stress, we can try to add more boundary condition, and we can specify that this particular location it should contain more material so that it can withstand the higher stress. After a few iterations we reach this type of design. This is a slightly modified version of the previous one, and here if we do the same FE analysis, we see that most of the things are green or light green, where it is still within the acceptable limits of the stress. So this is how we can modify the original design uh, through topology optimization to reach a new design where the material consumption is very less, and it can still withstand the load that the material is expected to take. Now another use case is how we can use AR VR. Now, for this, we can see what we mean by augmented reality and what is virtual reality. So, uh, we say augmented reality is because uh, to the our environment we add something, that is addition. That augmentation basically literally means we add few objects to our current environment. So that in that sense it is called augmented reality. And as I said, it is 75% real, 25% virtual. So 75% real means our environment remains as it is. We just add few things to virtual objects to our environment. That's why it's 25% virtual. So you can imagine this as we just want to add a sofa set to our home. So what we can do is we can add a virtual sofa set to our home. In that case, that sofa set is the virtual thing only, and our home remains the original real thing. So that way it is 25% virtual and 75% real. But in virtual reality, that is VR, it is mostly 75% virtual. So our environment is transformed into a virtual environment, and few things are real. Few things means few surrounding objects are real. Other than that, most of the other things are virtual in nature. So that's why the comparison is in VR, 75% things are virtual, but only 25% or less than things are real. So an example is AR partially immerses the user in the action. So as you can see, we can we can create some AR tools on our mobile phones also. So in that sense, using that mobile phone, we can create some virtual objects that would act on our environment, but it would be very limited in nature. So AR creates a partial immersive
ଘଣ୍ଟାଏ ପଳା
experience.
ମୋର 6 GB 6.100 MB ପଳା 100 MB
So I think there is some
730
noise.
ଆରି କୁଇଜ ଟେଷ୍ଟ ଅଛି।
Hello.
Just a minute.
Hello.
Dear
Yeah.
participants, please mute your system. Dear participants, please mute your system.
Okay, now it's much better. So yeah, in VR case, so what happens is it creates a fully immersive experience. So most of our surroundings get converted to uh, a virtual world, basically. So as we say, AR overlays, and another differentiator is AR overlays graphics and animation on top of real world environments. So those graphics and animations can be a 3D object or some other types of animations that gets added. But here creates a new simulated reality. So it would feel like we are in a different environment altogether. So how we enable this AR VR? So AR can be enabled through mobile phones. We don't have to use any other separate tools for it. But for VR, there are separate VR tools available that we can use for that to enable those VR experience, because it transforms the environment completely. That's why it is needed. It needs a separate VR tool. Now here we'll show one example how VR works in HP specific case. I'll play a video. Just let me know if the audio is visible or audio is audible or not. Is the audio there of this? Is it audible, or I'll have to share audio?
Sir, it is not audible, sir.
Oh, it's not audible. Okay, uh, uh, I'll maybe reshare. Just give me a minute. I'll,
ଥିଲା ସେ ସମସ୍ତଙ୍କୁ ଡାକି ହୋଟେଲରେ
yeah. Okay, I'll play the video. If it doesn't work, maybe I can do a voiceover of this. So I'll voice over it. I think it is not audible. Uh, so how this works is these are the tools basically that people use in 3D in HP 3D printers. So I'll just play the video and then I'll go to these specific things, and there is subtitle also. You can read things. So as I'll just go a few things. So like this. Uh, these tabs, like which things to modify, what is the instruction, these things come in the VR tool itself, and that helps the user or the maintenance engineer to fix those problems. So I'll just play over this. So here the steps what needs to be done after one, two, these steps are also mentioned. So first we have to wear that gear. And these all are software controlled. So yeah, by the these are actual 3D printers. So these are very big printers. Yeah. So here it will show, the person would show how to do some maintenance activity in the printer by following some outside instructions. So basically here that other person is able to control this, and by helping it out, they can fix that printer issues or whatever maintenance activity is required. So this is how that other steps and other things are coming in the VR tool. So using that, it is the person can easily fix those issues. Now next will so next we'll go to cyber physical systems, how this gets used in industries. So as I said, cyber physical systems basically means creating a digital replica of a physical systems. So our physical asset may be a aeroplane. Now we want to create a digital replica of it. Why do we need this? Because sometimes we want to monitor few things in the actual asset, and doing that might be a costly affair, because let's say you want to collect data on how that different sensors or different parts of the aeroplane behave when it is in operation. So for that, to get the data, we have to run multiple flights between different places to get the data. That becomes costly. But if we create a digital replica, we can run multiple simulations over this, and still we'll be able to collect the data whatever we need. So as I said, this digital twin concept helps during product development stage also. It can also help during production and support and services as well. So uh, we'll see one example how that helps. So first, there is a physical plant. There we some sensors are attached, and we collect data continuously from that. Now that sensors, there are some controllers, some electronics processes are there. Now once we collect the sensor data, that some algorithms are applied, like real-time sensor data is processed, and some anomaly detection algorithms or some near-time algorithms for resiliency. Resiliency means that system is running as per the expectation or not. So those kinds of logics that can be applied. So simultaneously, there is a replica of the physical plant, that is a model of the system basically. That is this multimodal multidisciplinary features. Using that, we build a digital model of the system, and once we have that system, we that system also gives us some data. So now we compare the data that we get from the digital replica as well as from the physical plant using the sensors, and based on that, we do that analysis, and we pass it back to the actuators. And here actuators means based on the actuators, we perform some actions. If let's say some value or some knob needs to be decreased, then we apply that action so that the engine operates or the machine operates within the required limits. So here it is called digital ghost algorithm because this works as a cybersecurity layer between the actual plant and the software replica. So here one advantage of this having this digital replica is once we fine tune this model, then based on the output of the sensor data, we can suggest some outcomes or actions for the physical plant. Even though the plant doesn't experience that rightly, we can using this replica we can predict what would happen to the plant given these conditions, give sensor conditions, what would happen let's say 5 years down the line or 5 months down the line. So this is how the digital twin concept helps. Now we'll see one example how HP is using this digital twin concept. So as we have seen in 3D printing, we there is a 3D metal printing in this case. There is a binding agent is there. We spread the powder, we put the binding agent, then we create a green part. And after green part is created, it goes to sintering. And after sintering, we get the solid part. So what happens in sintering is the microstructure of the part changes here because it is subjected to high temperature in the range of 600 to 700 degree temperature depending on the material that is getting used. So currently it is still is used. So that's why it is more than 600 700 degrees centigrade, the temperature goes to that range. Now why do we need sintering is because after sintering is done and then we do that cooling, the dimensions of the object change. If this is our original part, for example this dragon, so first it shrinks in dimensions after sintering because sintering increases temperature, it basically changes the microstructure, and after cooling also the material shrinks even further. So shrinking happens, there is also sag happens. So sag basically means towards the lower portions the volume increases little bit, and then there is some bending also. So sometimes the parts bend because of this sintering. Now this because of this the dimensions also change. Now can we incorporate these things at the design stage itself? So for that to happen we have to know how much by how much this each individual dimension should change when we do the sintering. And here it is not that straightforward because this is a very complex geometry. There is no length, width, and height here, so that there are many design parameters that we have to modify to create a actual geometry that is satisfying the dimensional tolerance also. So for that what happens, HP has a tool called digital sintering tool that works as a digital twin. So first we try to, let's say for example we want to design this part with 71, which length is 71 millimeter is size. Now uh, what happens after shrinking happens, so usually shrinking happens greater than 10% as linear size. So this becomes, as you can see at the right, this was the expected part, for example. Now after sintering this is how it looks. It has this length has shortened and also it is slightly bent with now, and because of that this is not acceptable. So we have to design our part such that after sintering it should be the like the right one with straight, it would be a straight part along with its dimensions as per the specification. So what this tool does, while designing itself, it creates a bend in the reverse direction so that when sintering happens, after sintering it will bend again a little bit, and it would adjust. So this pre-bend, after sintering there would be another bend, so both of this would cancel out. Then after sintering we'll get a slight straight bar. So these kinds of adjustments are happening in digital twin of the sintering machine. So what it essentially does is it has built a model of how sintering actually works based on in the sintering tool what is the environmental condition inside and what is the temperature range to which it is subjected to, what is the boundary conditions of these things, and what is the material on which sintering is applied. All this info gets passed here, and some previous history of data, because HP prints thousands of parts every month or every day. So those things, those info gets passed to here. Now that using that info, we come up with the design changes, and so that this we apply extra bend here, we slightly increase the length of the parts, so that after sintering, it would, whatever we get is actually a straight part and within the dimensions. So this is one application of that sintering, the digital twin concept that we used. So whatever we do in the software phase is completely independent of what is happening in the sintering, but still using this data, we can make design decisions, so that after sintering we get a perfect parts. Now last I would be focusing on is that there is a automation part. So how HP automation happens. Whatever we have seen is, uh, I'll just move to the beginning. We saw one build unit. So basically, this build unit has to be moved to a printer for it to get printed. Now, after printing ends, let's say after 11 or 12 hours, it has to be removed from that tool, from that engine. So for this, inserting this build unit and removing this tool unit, right now human labor is required, so that adds extra cost. And there is no easily, it has just to be inserted here, and it has to be inserted in powder unit at some point, then moved back from the powder unit, inserted again in the printer. So these things can be automated. So HP is also collaborating with Siemens to do this kind of automation. So I'll now play this video. I'll also do a voiceover. uh, So that D factory is the HP's 3D printing factory. Now what happens here is, so these are the robots basically. They carry the build units. They basically drag those build units, and based on the availability of the printers, they would be inserting. It will show. Yeah. So this empty built unit, it get inserted into a powder filling station, so that it would automatically be powder would be filled. Now after the build unit is loaded, it is again passed to the printer. Now this is how it gets to the printer. So that robot knows which printers are available, which printers are free. This is how the location looks like. So after that, the printing happens, printing starts. So once printing is done, then also that robot goes, it adds another build unit and removes the original build unit, so that the printing happens 24/7. And it moves that already printed parts to unpacking station. And everything is tracked, so that the robot knows which build units are available, which units will be available at what point in time, and what is their location. So everything can be tracked, so that we can get maximum efficiency out of the printing. Printing never stops, and no human intervention is required. So it is in collaboration with Siemens. So it is already under progress. uh, so this is how automation works in 3D printing industry, and this is how it helps in stopping or in improving the efficiency and that surface finish as well. So this stops. So these are the references that I've used in this talk. So yeah, I think yeah. Any questions anyone has?
Dear participants, please ask if you have any queries, please ask. Any queries? So perhaps there is no queries. Dr. Biswajit, we are very much thankful as you are with us, and really this session is very interesting and informative, and we can imagine, or also you can feel that how the smart manufacturing or smart industry 5.0 4.0 is really applicable in the smart factories or smart industries. So thank you very much.
Yeah. Thank you, ma'am.